Hi, I'm Xinyi. I'm a second year PhD student from Loughborough University. So today I'll be giving the presentation on multi-objective optimization using hybrid surrogate model in the application of hydrocracking process. So this presentation will cover the introduction, model development, result and discussion, and finally the conclusion. So let me start my presentation by explaining what is a hydrocracking process. So a hydrocracking process is a well-established oil treatment process, and the reaction is taking place along the packed bed reactor and undergoing a series of chemical reaction, but mainly cracking reaction, and to produce the short hydrocarbon molecule from a long hydrocarbon molecule in the presence of catalyst, and its typically carried out in the temperature range about 300 to 550 degrees Celsius. However, hydrocracking is a highly complex process which affected by numerous factors such as inconsistent feedstock, catalyst degradation, and operating condition. In addition, there are multiple economic and environmental factors such as quality and yield of product that must be considered during an optimization as well. This non-linearity behavior and underlying interaction make it difficult to predict and optimize in the hydrocracking process. Therefore, there is a need to develop a powerful predictive and optimization model. So now let's talk about the multi-objective optimization. As I mentioned before, there are multiple factors that should be considered during the optimization. And these factors, or we call it objective functions, are usually conflicting. So here we are using the NSGA in this multi-objective optimization problem, which are designed to converge on the Pareto front using Pareto ranking and crowding distance computation. And this algorithm is able to identify the trade-off curve between the objective functions. However, the effectiveness of this optimization model is still depending on how good is the surrogate model. So a surrogate model is actually an approximate model that maps the process inputs to an output. It is also provide an inexpensive and faster modeling method to suggest the next point evaluation instead of using the real process or experiment, which is always costly and time consuming. So there are two types of modeling methods in the hydrocracking process. They are first principle model and machine learning. So in hydrocracking process, the common first principle model is continuum lumping kinetics. It reflects the reaction phenomena with a clear physical meaning and strong traceability. While in machine learning, the common algorithm that used is artificial neural network, ANN, and it can resolve effectively the relationship of inputs and outputs with a short computational time. However, there are some drawbacks on the first principle model and machine learning model as well. For the first principle model, it needs simplified assumptions and neglects some factors selectively, which result in the lack of accuracy. And the modeling cycle is usually quite long as well. While for the machine learning, it's just a black box and the description of the mechanism is not clear and with poor interpretability. And this model is highly depending on the quality and quantity of data. So what we are doing is to fill the research gap and overcome the shortcoming in both models. We propose a novel strategy to hybridize the data-driven framework with mechanism-driven model to create a new gray box that can significantly improve the interpretability and traceability of the model. So that's all from the introduction. Now I'm going to talk about the model development. So in this project, the model framework is divided into two parts. There are hybrid surrogate model and the optimization model. So here, our hybrid model is developed from the integration of continuum lumping kinetics and the artificial neural network. And the continuum lumping kinetics describe the kinetics behavior of the lump with similar chemical properties such as boiling point and the carbon number. A linear equation is used to calculate the kinetic parameters from the process parameters, and then mass balance equation is used to calculate the product distribution. And from this continuum lumping kinetics model, in total 625 database was generated, where each data consists of 4 study parameters and its corresponding product distribution. So before using as a training data in the ANN model, this simulation data is validated with the experimental data with similar operating condition, which you can see at the left bottom here. And the results has proven the reliability of the model data, and it's readily to be used as a training data for the ANN model. The second part of the hybrid model is artificial neural network. A simple backpropagation ANN model with single hidden layer is used in this study, and each hidden layer consists of 10 nodes, and the model has 4 inputs and 70 outputs. The activation function here is the sigmoid function, and the desired error is set as 0.01 with the learning rates of 0.05. And the database is divided into 2 parts, and 80% is used for training and the rest 20% is used for testing. Now let's have a look at the result of this model. So figure A showed the training progress for the first set of data, where the mean square error less than 0.01 is achieved after 1,600 iteration. And the figure B showed the error function behavior for the rest of our data. So that was the hybrid surrogate model, and now is the second part of the model framework, which is multi-objective optimization. And this diagram shows the flow chart of the optimization by using the NSGA algorithm. And the previous well-trained hybrid model will be used as the evaluation function in this multi-objective optimization. And in this project, the objectives are to maximize the short chain component from carbon 1 to carbon 22 and to minimize the long chain component from carbon 23 to carbon 70. And this objective will be optimized at the same time. So now I'm going to talk about the experiment background. And this experiment was actually carried out by Adam in 2012. And here is the schematic diagram of the hydrocracking process. So the feedstock that we use is the fixture Tropsch wax, and the hydrocracking is carried out in the packed bed reactor, and the catalyst that we use is the platinum with amorphous silica alumina, and the product from the hydrocracking process is analyzed in GCMS. The experimental data here is used to validate our model data. In this section, I'm going to show you some of the results from the hybrid model and the optimization model. Here, the hybrid model is used to study the effect of temperature on the hydrocracking performance. Different temperature was studied from 324 to 354 degrees Celsius. At the same time, the other operating conditions are kept constant. As you can see from figure A and B, as the temperature increased, the concentration of long chain component decreased. At the same time, the concentration of the short chain component increased. This is because a higher temperature results in higher rates of hydrocracking. And based on the figure C, the conversion increased approximately of 26% when the temperature increased from 324 to 354 degrees Celsius. And then now let's have a look on the effect of pressure on the hydrocracking performance. So different reactor pressure was studied from 40 to 54 bar. As you can see from the figure, as the pressure increased, the concentration of hydrogen increased, which in turn increased the rate of hydrogenation instead of increased the rate of cracking. And from figure B, the conversion decreased with increasing pressure after 45 bar due to the increase of the fugacity of hydrogen that will negatively affect the dehydrogenation equilibrium of the feed. So that was the result from the hybrid model. And now let's have a look at the result from the multi-objective optimization by using the NSGA. So the objective of this study is to maximize the short chain component and minimize the long chain component at the same time. And the range of the operating parameter that used in this optimization model are listed in the table below. So we can see from the figure A is a Pareto front that found by the algorithm. A decrease in the long chain component is at the cost of an increase in the short chain component. The Pareto front is able to identify a trade-off curve between the concentration of desired product and the side product. And this provides an information to assist the active learning process during the process design. And figure B shows the optimum parameters in the 4D space corresponding to the Pareto front in figure A. And based on the objective of the study, a maximum concentration of short chain component 77.6% with a minimum concentration of the short chain of 23.8% are achieved, and the corresponding optimum parameters are 353.9 degrees Celsius and 45.5 bar in pressure and 0.1496 in the ratio of hydrogen to feed, and finally 2.94 for the residence time. So, in the conclusion, I would like to summarize all the work and the result. So this study proposed the idea of using hybrid model as a surrogate model in the multi-objective optimization. Initially, we have used a verified continuum lumping kinetics model to generate 625 times 74 database. And this data is then used as a training data in the ANN model. And based on the result of the ANN model, more than 0.99 of correlation coefficient is achieved. And this well-trained hybrid model is then used as the surrogate model in the multi-objective function. And based on the result of the optimization, maximum short chain component of 77.6% is achieved from the Pareto front. And this model provides a fast and accurate prediction and optimization as well. Before I end my presentation, I would like to say thank you for my supervisory team from Loughborough University and Heriot-Watt University for the guidance throughout this project. So this is the end of my presentation. I would like to say thank you again for the organizer from International Conference on Energy and AI. And if you have any question, please drop me an email. Or if you are interested on my future research work, please follow me on my Twitter and LinkedIn. Thank you.